So now, having looked at the parallel load case, we also look at another very important feature of a register, which is basically the shift register. Okay, the shift register is very interesting because what I basically want to do now is, instead of connecting all these registers in parallel like this, I could also choose to chain these registers serially. Okay, this is again my 4 D flip flops, and I'm just going to connect the output of one. This is D, Q, D, Q, and I have 4 clocks. Okay, and what I can do is, I will just call this SI. I just call it I. Okay, and an output uh, O, right? Or let me call it. Let me just call it, no, not Q, because that can confuse with the Q of the flop. So I will call it I and A and Y. That will be easier. Yeah, A and Y. Okay. So what has happened is, Q0 bit, this Q0 bit, okay, I could still have this system give me 4 outputs. Okay, this is Q0, Q1, Q2 and Q3. Okay. What this is going to do is, it has cut access to all the internal nodes. Okay, so if I look at this black box here, if I look at this black box, right, whatever signal is coming out of that box is what is available from the outside, right? So I cannot access anything internally, this thing. So for example, I cannot access the input D, I can't do a parallel load here. Okay, the only access for me is through the input A, and therefore if I have to reach Q3, right, or D3, the only way I can do that is to actually go serially from one flip flop to another by through the clock. Okay, so therefore this one is a slightly different case. It is specifically useful in cases where we want to access everything using just one pin, but using a serial operation. However, the data output from the queues is still available in parallel as Q0 to Q3, right? So for example, let's again look at what happens when you actually do this kind of an operation. Okay, so I'm going to look at the clock edges as usual. Right, I need at, so I'm going to take more than 4 cycles now, because okay, this is clock, this is my input A. Okay, what I'm going to do is, I will assume that I want to initialize this in the following manner. okay, or the last one I will continue it as 1. Okay, so assume that my input A is making a transition like this, okay, and I am going to look at the output Q 3:0. Okay, so this is a 4-bit output but a single bit input to this system. So therefore, I have to look at this, as a bus. Okay, this is n equal to 1, n equal to 2, right. So when you power on this system, the states of Q0, Q1, Q2 and Q3 are random, right. Each flop can turn on in some arbitrary state, 0, 1 state, which we don't know. It could be all zeros also, but we do not know what that state is. And therefore, my output for Q, so this time I am going to draw it as if there is absolutely no delay. That means as soon as the clock hits, you will see a transition. Okay. Now, the fact is that this is an unknown state. Why? Because Q3 to 0 are all unknown bits. It could be random 0 or 1. I have no idea what it is. What happens now when the first clock edge comes is the data is taken from A and it is made available to Q0. Okay. However, Q1, Q2, Q3, what has happened is data from Q0 has gone to Q1, Q1 to Q2, Q2 to Q3, right? And effectively, the unknown state of Q0, Q1, Q2, Q3, has simply moved to the right by one step, and therefore Q1, Q2, Q3 are still unknown, and therefore even here, right, I will have to say unknown state because I do not know what Q1, Q2 and Q3 are. Okay. Now, by the same logic, it does not matter, what happens to, it does not matter what the data is. The next cycle, again, Q0 was already initialized correctly. That will now go to Q1. Therefore, we know what Q1 is, but Q2 and Q3 are unknown. Okay. Now, the point is this unknown state will keep changing clock cycle by clock cycle because data is shifting, right. Therefore, this will still continue to be an unknown state. Okay. And right. So, now here, right. So, what will happen is finally after n equal to 4 cycles, right, you have been able to initialize all the nodes in that serial shift register appropriately. Okay. So, what does this mean? It means Q3:0, okay. Q3 is the output. So, what was sent as at n equal to 1 is what will appear at Q3 after 4 cycles, right. So, Q3 will basically be 0. So, whatever you see here, this is what Q3 will get initialized to. This is what Q2, Q1 and finally Q0, whatever the value of A is, right, and therefore this will be 0, 1, 0, 1. Q3 to 0 will be 0, 1, 0, 1 out at this point. Okay. And finally, like I said, we have been able to initialize all the nodes to known values appropriately. Now, when I continue to do this operation, right, and other, 1 has sort of appeared here, sorry, at this point at n equal to 5, at this point a new 1 has entered the system, and therefore uh, the data will actually shift like this, right, and therefore you will have q3 colon 0 equals 1 0 1, but what entered the system is another 1, and therefore this will be 1. Okay. So in this manner you will be able to essentially serially load data, okay, into the shift register like this, okay, and so this is basically sort of like a queue, right? You send in data and then it comes out at the other end of the queue after n clock cycles, depending on the number of flops that we have added there, okay. Now I could choose to modify this a little more, right? I could choose to do something very interesting here, where I say I want to combine the serial operation along with that parallel operation that I discussed earlier, okay. For example, normally I would be doing some parallel load of data, but in under a special condition, when load equal to 1, I want to load data into this into this flop parallelly, but once I load it, I want to scan it, I want to shift it out serially, right. So that is my aim. So pseudo code again, if load equal to 1, okay, this is a parallel load serial shift. Okay, so if load equal to 1, I want Q3 to 0 to be equal to I. Okay, else I want to shift data out like I did the serial shifting operation. Okay, so obviously, like I said again, the moment you have an if condition in your pseudo code or the algorithm, the simplest way to do this is to actually implement it with a multiplexer, right. So therefore I'll consider this okay, and this is D0, D1, right, clocks are here. Okay, and so what I'm now going to do is I'm going to put a multiplexer before these guys. Okay, before each of these guys, I'm going to draw a 2:1 multiplexer. Okay, so this is DQ, right? DQ, DQ, and Q. So here, so remember in the earlier case we did parallel load or hold data. In this case we are either parallel loading or we are shifting data out, okay. So let us look at this. I am going to control this multiplexer with load, okay. If load equal to 1, then I want to load data from this thing, from some parallel data. This is I0, and so I will call this A and Y, okay, as usual. I1. So this is what I am going to do here. Q is like this. So this is 1 and this is 0. 1 0 1 0. I2. And I3. Yeah, 1 and 0. Right? And the multiplexer input is obviously load. Okay, and my outputs are obviously, as usual, they are available to the outside world. So I'll move this clock. Q0, Q1, Q2, Q3. Okay, so now with respect to this, what is happening is when the load is equal to 1 on all 4 flops, the multiplexer's arm where the input can be fed in gets activated, and therefore those 4 inputs will be made available at the output when the clock pulses, right? When the clock samples the data, and then you can do some serial operations and the data will actually move, right? So you can again, it's important to be able to draw these timing diagrams appropriately here. Okay, so as usual, I will start with the clock. So some initialize 1, 2, 3. No, I need more space, so I'll probably go to the next page. Right, so I'll keep this on top here. Okay, and then I will load this. N equal to 1 in red, N equal to 2, N equal to 3, 4. N equal to 5. Okay, so we'll look at this, and we are now going to look at what happens when my I 3 to 0, okay, is, I'm going to initialize this. Okay, and unlike the earlier case, I'm going to initialize very specifically with I equal to 1 0 1 1. That is I3. So maybe I should say I3:0. That is I3 to 0 is 1 0 1 1. That means I3 is 1, I2 is 0, and the other 2 bits are also 1. Okay, and then here doesn't matter, my I can change to whatever is needed, to whatever is, it can go to any state. My load signal is going to activate like this. Okay, it goes high just before the clock edge, and then it remains low after that. right? So the load never goes high, okay? So what happens is, now I am going to look at Q3 to 0 here, right? So let's look at this as usual. Okay, so Q3 to 0 is, of course, we do not know what it started off with, right? Likewise, this is state 0. I don't care about that. This is specifically, this is state 1. This case, I am considering 1011 as the input, as a specific example, right? And therefore, what will happen is, the moment the clock samples the data at sampling edge n equal to 1, right, I3 to 0 will simply appear, load has gone high at the input to the multiplexer, and therefore the data which has already settled to 1011 is also available, right? So if you look at this, we are talking of 1011. Okay, that data will just get loaded and appear here. So my Q of 3:0 will be 1011. So it will simply appear at the Q at the first clock edge. Okay, now we'll see what is going to happen. So unlike the previous case where it took us n clock cycles to initialize the outputs to a known state, right? Here we are able to do this in just one clock cycle using this parallel load idea, right? So if we do this, we get 1011 at the output for Q3 down to 0, right? And we are going to now see what happens as the data is now shifted out. Load has gone 0 after that. That means only the 0 path of the multiplexer will be accessible always, okay? And I am assuming in this entire exercise A equal to 0. Okay, I am not changing A at all. So that's why I am not even going to show it, or I might just show it here. A signal is 0. Right? A equal to 0. Right? Just to see, just to not complicate this timing diagram. So now at the next n equal to 2, data will start shifting out. Okay. So this Q3 was initialized. So if you look at this, it was initialized on the first clock cycle 1 0 1 1. Okay. And what will happen at n equal to 2? In fact, I could even color code this interestingly. Okay. So let me remove this color coding and just call it A equal to 0. I will color code these edges. Okay, this is n equal to 2. This is n equal to 3. Right? And this is n equal to 4. And this is n equal to 5. Okay. So my Q3 to 0 starts with 1011. Okay. 1011. Okay. Now the Q3 is overwritten by Q2, right? So data will become, Q3 will become 0 in the next cycle. Okay. 0, 1, 1, and A is 0, so you will get 0 here. Okay. So in the next cycle, my data will simply become 0, 1, 1, 0. Right? And at n equal to 3, again that 0, Q3 equal to 0 goes away, it gets overwritten by this thing. So here this will become 1, 1, 0, 0. Okay. So if you look at so Q3 is 1 1 0 0, right? Then sorry, oh, I'm sorry, this is not correct. I used the wrong color. This should not be green. Yeah, sorry. This should be 0 1 1 0, right? And n equal to green. Yeah. So this is in green. It is going to become 1 1 0 0. Okay. And oh, not green again. Sorry. In purple, 1 1 0 0, right? Then in green, it will become 1 0 0 0, right? And finally, after n equal to 5, it will become 0 0 0 0, right? So in order to get Q0 out, right, you are going to need 4 clock cycles after you initialize. That's why from n equal to 2 to 5, it takes for Q0 to go from that starting point to the output of that shift register, right? So if you just, I mean, it may be useful to put these numbers down here. You just see the shifting operation 1 0 1 1, 0 1 1 0, 1 1 0 0, 1 0 0 0, and last one is 0 0 0 0. Okay, this is my Q3, Q2, Q1, Q0. Okay. Yeah, so this is also important to note that the shifting direction in the shift register could happen in one way, but when we represent the data, it could happen the other way, right? There's no hard and fast rule that both of those should be the same. So if you look at it, the shifting happens in this direction. Okay, Q0 going to Q1 to Q2 to Q3 and so on. So with that, what we have been able to do is to implement a very, very interesting structure called the parallel in serial out shift register.